Welcome to the world of signals and systems. In this course, we'll explore the fundamental characteristics of signals and systems, understand how they operate in both time and transform domains, and develop mathematical skills to solve problems involving convolution, filtering, modulation, and sampling. Our journey will be supported by key textbooks and web resources, ensuring a comprehensive learning experience. Whether you're new to the subject or looking to deepen your understanding, this course will provide the essential tools and perspectives needed to analyze and interpret signals and systems in various engineering contexts. Let's begin by setting the stage for what's ahead. Signal is any physical quantity that varies with time, space, or another independent variable. Essentially, anything that carries information can be considered a signal. For example, the human voice, the chirping of birds, temperature changes, smoke signals, signals in telephone wires, or even the fragrance of flowers, all are signals in different forms. Signals are the backbone of communication and information processing, and they can be found everywhere in our daily lives. Understanding signals is the first step toward analyzing how systems process and respond to them. Let's look at some real-world examples of signals. The human voice is a classic example, as it varies in amplitude and frequency to convey speech. The chirping of birds is another, where the sound patterns change over time. Temperature readings, smoke signals, and even the scent of flowers can be considered signals because they change and can be measured or detected. In technology, signals travel through telephone wires or are represented as electrical impulses in circuit. These diverse examples highlight how signals are integral to both natural and engineered systems. Signals are often expressed mathematically as functions of independent variables, usually time. For instance, a signal xt might be defined as having a certain value within a specific time interval and zero elsewhere. This mathematical approach allows us to analyze, manipulate, and process signals systematically. By representing signals with equations, we can predict their behavior, combine them, and apply various operations, which is essential for engineering application. Signals can depend on one or more independent variables. If a signal depends on only one variable, such as time, it is called a one-dimensional signal. Examples include audio signals or temperature readings over time. If a signal depends on two or more variables, such as images which depend on both x and y spatial coordinates, it is called a multidimensional signal. Understanding the dimensionality of a signal is crucial for selecting the right analysis and processing techniques. System is an interconnection of different physical components that act together to perform a specific task. In the context of signals and systems, a system is any device or process that takes an input signal and produces an output signal. For example, a motor converts electrical energy into mechanical energy, an amplifier increases the strength of a signal, and a filter removes unwanted frequencies. Systems are everywhere, from simple household devices to complex communication networks. Relationship between a system's input and output is fundamental. For a given input signal xt, the system applies an operation to produce the output yt. This operation could be as simple as scaling the input or as complex as filtering or modulating it. Understanding this relationship allows engineers to design systems that achieve desired outcomes, such as enhancing audio quality or transmitting data reliably. Continuous time signals are defined for every value of time and are typically represented as xt. These signals can take on any value at any instant in time, making them ideal for representing natural phenomena like sound, temperature, or voltage. Continuous time signals are the foundation for analog systems and are often visualized as smooth, unbroken curves on a graph. Discrete time signals are defined only at specific, separate points in time, often represented as xn. These signals are common in digital systems where information is processed in steps or samples. Examples include digital audio recordings or sampled temperature data. Discrete time signals are visualized as sequences of points rather than continuous curves. Signals can undergo various basic operations, including time shifting, scaling, and reversal. Time shifting moves the signal forward or backward in time, scaling changes its amplitude or time axis, and reversal flips it around the time axis. These operations are essential tools for analyzing and manipulating signals, allowing us to align, stretch, compress, or invert them as needed for different applications. Time shifting involves moving a signal along the time axis. If we delay a signal by a certain amount, it appears later in time. If we advance it, it appears earlier. Mathematically, this is represented as yt xt k for a delay or yt xt plus k for an advance. Time shifting is useful in applications like signal synchronization and echo effects. Amplitude shifting changes the vertical position of a signal by adding or subtracting a constant value. For example, yt equals xt plus k shifts the entire signal up or down by k units. This operation is often used to adjust the baseline of a signal or to prepare it for further processing, such as normalization or thresholding. Scaling operations modify either the time axis or the amplitude of a signal. Time scaling compresses or stretches the signal along the time axis, while amplitude scaling changes its height. For example, yt equals x compresses the signal if a 1 and stretches it if 0 or 1. Amplitude scaling yt at xt increases or decreases the signal's magnitude. These transformations are crucial in applications like audio processing and image resizing. Signal reversal flips a signal around the vertical axis, effectively reversing its direction in time. Mathematically, this is represented as yt equals xt. Reversal is useful for analyzing symmetry properties of signals and for certain signal processing techniques such as convolution. It helps in understanding how signals behave when time is inverted. There are several elementary continuous time signals that form the building blocks for more complex signals. These include the unit step function, unit ramp function, unit impulse, unit parabolic function, rectangular and triangular pulses, signum, sinc, Gaussian, sinusoidal, and exponential signals. Each of these has unique properties and mathematical definitions, making them essential for signal analysis and system design. Unit step function, denoted as UT, is defined as 1 for t greater or equal to 0 and 0 for t0. It represents a sudden change or activation at time 0 and is widely used to model systems that turn on at a specific moment. The discrete version UN is similarly defined for sequences. The unit step function is fundamental in system analysis, especially for studying system responses to sudden input. Unit ramp function, RT, increases linearly with time for t greater or equal to 0 and is 0 otherwise. It's like a ramp that starts at 0 and rises steadily. The ramp function is the integral of the unit step function and is used to model systems with gradually increasing inputs, such as charging a capacitor or accelerating a vehicle. Sine wave is a periodic signal that oscillates smoothly and is fundamental in representing alternating currents, sound waves, and more. Its mathematical form is xt, a sin omega plus phi, where a is amplitude, omega is angular frequency, and phi is phase. Sine waves are building blocks for more complex signals and are key in Fourier analysis. Unit parabolic function is defined as pt equals t22 for t greater or equal to 0 and 0 otherwise. It's obtained by integrating the ramp function and is used to model systems with accelerating responses, such as the displacement of an object under constant acceleration. The parabolic function is another essential building block in signal analysis. Rectangular pulse function, often called the gate function, is defined as 1 within a certain interval and 0 elsewhere. It's used to represent signals that are active for a limited time, such as digital pulses or time windows in sampling. Rectangular pulses are fundamental in digital communication and signal processing. The triangular pulse function rises and falls linearly, forming a triangle shape. It's used to model signals that increase and decrease smoothly over time, such as certain audio waveforms or window functions in signal processing. Triangular pulses are useful for smoothing and shaping signals. Signum function, SGNT, indicates the sign of a value. It's 1 for positive, 0 for 0, and -1 for negative values. It's used in mathematical analysis to separate positive and negative components of a signal and is helpful in defining piecewise functions and analyzing symmetry. Sinc function is defined as sinc t equals sin pite for t not equal to 0 and 1 for t equals 0. It's a key function in signal processing, especially in sampling theory and reconstruction of signals. The sinc function's unique shape allows it to act as an ideal low-pass filter in theory. The Gaussian function is defined as gt equals e at 2, whereas 0. It's widely used to model noise probability distributions and smooth pulses. Gaussian signals have the unique property of being smooth and rapidly decaying, making them ideal for applications in communications and statistics. Continuous time sinusoidal signal is given by xt, a sin omega plus phi, where a is amplitude, omega is angular frequency, and phi is phase angle. Sinusoidal signals are fundamental in representing periodic phenomena, such as alternating current, sound waves, and radio signals. Their properties make them central to Fourier analysis and signal decomposition. Exponential signals can be real or complex. A real exponential signal is xtaet, where the sign of a determines if the signal grows or decays. Complex exponentials xt equals e sigma plus j omega t combine exponential growth decay with oscillation and are fundamental in analyzing system responses and frequency content. Signals can be represented mathematically using combinations of elementary functions such as steps, ramps, and pulses. By shifting and scaling these basic signals, we can construct complex waveforms that model real-world phenomena. This approach is essential for analyzing and synthesizing signals in engineering. Signals can be classified in several ways, as continuous time or discrete time, deterministic or random, periodic or aperiodic, even or odd, energy or power, and causal or non-causal. Each classification provides insights into the signal's behavior and determines the appropriate analysis techniques. Even signal satisfies xt equals xt, meaning it's symmetric about the vertical axis. An odd signal satisfies xt equals xt, showing anasymmetry. Any signal can be decomposed into even and odd components, which is useful for analysis and system design. Even and odd properties help in simplifying mathematical operations and understanding signal behavior. Signal is periodic if it repeats itself after a fixed interval t, such that xt plus t, for all t the smallest such t is the fundamental period. Aperiodic signals do not repeat. Periodic signals are common in communication and control systems, while aperiodic signals are often encountered in transient or random phenomena. Deterministic signals are those whose values can be precisely predicted at any time, such as a sine wave. Random signals like noise have values that cannot be exactly predicted and are described by probability. Understanding the distinction is crucial for designing systems that can handle uncertainty and variability. Causal signal is 0 for all times before t equals 0, meaning it depends only on present and past values. Non-causal signals depend on future values as well. Most physical systems are causal, but non-causal signals are important in theoretical analysis and digital signal processing. Signals are classified as energy or power signals based on their total energy and average power. An energy signal has finite total energy and zero average power, while a power signal has finite average power and infinite energy. This classification helps determine the appropriate analysis and processing techniques for different types of signals. Systems can be classified as static or dynamic, causal or non-causal, time-invariant or time-variant, linear or nonlinear, invertible or non-invertible, and stable or unstable. Each classification reveals important properties about how the system processes signals and responds to different inputs. Static memoryless systems output depends only on the present input, while a dynamic with memory systems output depends on past or future inputs. For example, a resistor is static, but a capacitor which depends on past voltage is dynamic. This distinction is crucial for modeling and analyzing real-world systems. Causal systems output depends only on present and past inputs, never future ones. Non-causal systems, in contrast, require future input values to determine the output. Most real-world systems are causal, but non-causal systems are useful in theoretical studies and some digital applications. Time-invariant systems' behavior does not change over time. Its response to a given input is always the same, regardless of when the input is applied. In contrast, a time-variant system's response can change over time. Time invariance is a desirable property in many engineering systems as it ensures consistent performance. A linear system follows the principles of superposition and homogeneity, meaning the response to a sum of inputs is the sum of the responses, and scaling the input scales the output. Nonlinear systems do not follow these rules. Linearity simplifies analysis and design, making linear systems a central focus in engineering. An invertible system allows you to uniquely determine the input from the output, meaning there's a one-to-one mapping. Non-invertible systems lose information, making it impossible to recover the original input. Invertibility is important for applications like encryption and signal recovery. A stable system produces a bounded output for every bounded input BIBO stability. If a system's output can grow without bound even when the input is limited, it's unstable. Stability is a critical requirement for practical systems, ensuring predictable and safe operation. Systems can be connected in various ways: series cascade, series parallel, and feedback. Each configuration has unique properties and is used in different engineering applications. For example, a radio receiver followed by an amplifier is a series connection, while multiple microphones feeding into a single speaker system is a parallel connection. Signal is absolutely integrable if the integral of its absolute value over all time is finite. This property ensures that the signal's total area is limited, which is important for certain mathematical analyses. Similarly, a discrete signal is absolutely summable if the sum of its absolute values is finite. These properties are essential for energy signals and system stability. Signal is square integrable if the integral of the square of its absolute value is finite. This property is important for signals that represent energy, as it ensures the total energy is limited. Square integrability is a key requirement in many signal processing and communication systems. Summary: signals and systems form the foundation of modern engineering, enabling us to model, analyze, and design everything from communication networks to control systems. Understanding the types of signals, their properties, and how systems process them is essential for tackling real-world engineering challenges. With these fundamentals, you're well equipped to explore advanced topics and applications in signals and systems. As we move forward, we'll dive deeper into the mathematical tools and techniques used to analyze signals and systems, including convolution, filtering, modulation, and sampling. These concepts will empower you to solve complex engineering problems and innovate in fields like communications, electronics, and control systems. Stay curious and keep exploring. The world of signals and systems is vast and full of exciting possibilities.